Yeah, so thanks everyone for coming. This is my talk, One Cluster to Rule Them All. I'm out on the cloud. Today I'll be talking about bridging the gap between your development environment and the cloud. Some of the challenges with running or managing a cluster in the cloud, and then a solution that we've come up with to kind of address those challenges. And finally, some takeaways at the end. Okay. So yeah, quick introduction about me. My name is Victor Yap. I'm an MLOps Engineer at Rev.com. At Rev, we build ASR and NLP models for speech recognition for our customers. I started with software engineering, and then I transitioned to DevOps, and now I'm working in MLOps. So that's just to give you an idea of where my background is. It's not from machine learning. It's more from a software engineering side. And I won't try to define what MLOps is, just that for our team, it does involve a lot of ops right now. We're a pretty small team, so we have to do a lot of the DevOps as well. So we manage a lot of the infrastructure. But something in DevOps that I want to try to bring through to MLOps is the idea of continuous improvement, building or delivering faster and delivering higher quality. And at first, those two may seem like they are opposed to each other, that you have to slow down in order to have higher quality, or that you might have to sacrifice quality to have, to deliver faster. But I think when you try to pursue both, you have to start building systems and tools that are that make you more productive. So my role in MLOps at Rev is to build systems and tools that help the machine learning engineers and data scientists to be more productive, which honestly I find pretty exciting, because then I can just focus on the infrastructure and the tooling, and then they can focus on machine learning, and overall we just can push the limits and the state of the art of what we're doing. And then one more thing I want to add is I'm most familiar with AWS when it comes to cloud providers. So just so you know, where the limits of my experience are with cloud. Okay, so that's enough about me. What I really want to talk about is the problem that is bridging the gap between your development environment and the cloud. So first, I kind of have a question for you all. Can you think of a situation where you're limited by your development environment, whether that's your laptop, a personal workstation, or VM? So when I say limited, what I mean is by the number of CPUs or how much memory you had, and you're working on a problem and you just don't have enough in your development environment. A common problem that I've seen, at least in our team with ML, is it takes a lot of resources to even just develop, whether you're working on a model or you're pre-processing a lot of data, and a lot of those resources just don't fit in your development environment. So that's where using the cloud comes in, because cloud providers have a lot of instances. They have gigantic instances with lots of CPUs and memory and GPUs. But the problem is, it's one thing to write a script that works on your laptop, because you're developing, and then you want to run that with the scale that the cloud has, and that's the problem I want to focus on, is how do you take something that you developed on your laptop and then running it in the cloud? And also making it as frictionless or as easy as possible, because the more barriers or the more friction there is to go from the left-hand side to the right-hand side, the less it will be used and just the less effective it will be overall. So by the end of this talk, I hope to present a simple interface for requesting resources from the cloud that works both in your development environment and some of the challenges of managing a cloud cluster. Okay, so what are the challenges in managing a cloud cluster? First of all, which may be an obvious one, is auto-scaling. You want to scale up your instances when you get more tasks that come in, when you have more jobs to run. And if you have less jobs to run, you want to scale them down. But really, you also want it to be configurable, because there's no like one-size-fits-all for these, for scaling. You may be willing to pay more for higher throughput. You may be willing to run more instances on all the time. Or on the other side, you may want to shut down instances sooner, save more on your costs, but it may take longer to run a job. So it should be configurable. Next is right sizing. So if you have a job that needs, let's say, 1 CPU and 2 gigabytes of memory, then you want to find an instance that fits for that. You don't want to use an instance type that has a lot of memory, because then you're just paying more for an instance type that doesn't fit your resource requirements. So there's a lot of instance types that cloud providers have, and one of the challenges is finding the right instance type for your workload. Next is in trying to use spot instances. So first of all, spot instances are just unused capacity in your cloud provider. So in AWS, for example, the advantage of using spot instances is they have huge discounts when you use them, 26 to even up to 90% than if you run it on demand. But the biggest issue is you can get terminated with only a 2-minute warning. So the challenge here is you want to use spot instances when you can, but how is that going to work in your cluster? And then you could argue that, well, we have enough money, we don't want to run, or we don't want to bother with the complexity of using spot instances. But I would still argue that you should, if you figure out that it's worth it, you should, because if on average a spot instance is 50% of a discount, then with the same budget you could run twice as many experiments or trainings or whatever you're running on your cluster. So it's still worth it to try. And before I talk about environment management, I just want to point out that the first 3 I've talked about are just about costs. Like, if you didn't worry about costs, then you could just run the biggest instances all the time on demand. So one thing with running, a challenge in using the cloud is optimizing for costs, and that's just a general theme with the first 3. And then lastly is environment management. So as a developer or someone who's iterating on a job to run, there's probably going to be some dependencies that aren't installed on the cluster side. So how, as a developer, do you make that easy? And one idea is you could pre-install all your dependencies in one image that the cluster will use, but now you have a bloated image with that would be slower to start, and you may have to update it frequently because you have a lot, anyone who introduces a new dependency, you have to update the image, and then different versions of the same library would be harder to support. So the challenge here is providing a way for the developer to specify their runtime and have the cluster either manage or create that. Okay, so the tools that we're going to put together are right here, Ray, which is a Pythonic library for requesting resources and running distributed applications. Kubernetes, which is a container platform for running containers across nodes. And Karpenter, which autoscales Kubernetes nodes just in time. It'll find best fit instances to run pods that can't be scheduled. And I'll go deeper into each of these 3, but I just wanted to start with a high-level explanation of each of them. I also want to just take a moment to thank the Ray community and the Karpenter community, because as I worked on this talk and as I've worked on these, worked in using these projects, they've been very helpful and active with answering my questions and just promoting an active community. And that's also another benefit of using open source tooling is they have strong communities that you can lean on whenever you need support. So, Ray. Like I said earlier, Ray is a Pythonic library, a simple universal API for building distributed applications. So there's two parts to Ray. There are clients, and then there's the cluster. And clients will submit tasks to the head node of the cluster, and then the head node will schedule those tasks to run on different worker nodes. And then within the cluster, or within it, there's another piece, which is the Ray Autoscaler, which will look at pending tasks and the resources that they're requesting, and then launch or terminate instances based on that, or launch or terminate workers based on that. So some alternatives to Ray, or just in general, some alternatives to a cluster are AWS Batch and Swarm. I just wanted to touch on these because these came up as we were surveying different tools to use as a cluster. And AWS Batch is AWS's managed service for running batch processing. It will also auto-scale and find the right instance type for your jobs. But the reason we're choosing Ray over these two is it's just not as Pythonic. And I'll show some code later to demonstrate like what it looks like to use Ray in your code. But if I wanted to use AWS Batch, and so I'm writing my Python script, and I want to launch a batch job, I have to like make some AWS API calls to launch the job, monitor it, wait for it to come back, and then continue the script from there. So that external interaction just kind of breaks the flow of the program. And so it just causes more friction overall. Yeah, so here's a slide with demonstrating what it looks like to use Ray. So with Ray, you need to start by connecting to a cluster, and that's done with ray.init. If you don't pass any address, or if you just call ray.init by itself, it'll start a local cluster on your current machine. But you can also give it the address of the head node, and it will use that as the cluster instead. And just for an example, when you use Ray, and let's say when you use Ray, you decorate Python functions with its decorator like this, so at ray.remote. And then within the decorator, you specify what are your resource requirements for that function. So in this case, I'm just assuming we have some kind of preprocessing function for data, and we need at least 1 gigabyte of memory for that. Also, there are different resources you can request, like the number of GPUs, or the GPU type, or accelerator type, which in this case would be a P2 type instance. So let's say in one script, you want to preprocess your data and then go to train, but different functions of that script need different resources. So this is one way that can all happen just in one file. Let's see. Next, I want to talk about Kubernetes. So the Ray worker nodes have to run on something. And in this case, we chose Kubernetes because it's generally, there's a lot more support for Kubernetes, and it's more flexible, and it makes it easy to take containers, like on the left-hand side, and find the right node for them. So Kubernetes is a broad topic, and I'm not really going to try to explain it all now. But the two, I guess, terms I want to make clear on is, in Kubernetes, there's the pods, which are just sets of containers. And for us, or for this talk, it's just really just like the worker nodes and the head nodes of Ray. And then there are nodes, which are the actual instances that the pods run on. So since we're using AWS underneath all of this, our nodes are just EC2 instances. One of the problems with, or one issue with using Kubernetes is provisioning and managing those nodes. So if we set this up and didn't touch it, then we would have a maximum capacity based on how many nodes we have. And so that is also what, so this is where Karpenter comes in, or any cluster Kubernetes node autoscaler Karpenter will, so if we launch some pods, like you see on the top left, there are some pending pods. Kubernetes initially will try to schedule those pods on your existing nodes. So that's in the middle. But there are going to be some pods that it can't schedule based, they just don't fit on all of the nodes. Or maybe maybe we have a pod that wants 16 gigabytes of memory and we just don't have an instance with 16 gigabytes. So Karpenter will look at those unschedulable pods and then launch instances based on that and add it to your cluster. So Kubernetes helps with finding a best fit instance type for incoming pods that can't be scheduled and just increasing the capacity of your cluster to run those pods. And as instances don't have pods running on them, Karpenter will also delete those nodes. So it's just a very dynamic way of creating EC2 instances as Kubernetes nodes and just finding the best fit instance type. So again, this is the problem of right sizing. Okay, so putting it all together, initially we have Array client, which could be your laptop. And you'll connect to your Array head node, which you can specify by an address. And the Array head node will take those tasks, and then the Array autoscaler will say, okay, well, there are a lot of tasks or just a lot of resource requirements that we need more worker pods for, Array worker pods. So that's where number 2 comes in. The Array autoscaler will launch more Array worker pods. And assuming there's not enough EC2 instances or essentially Kubernetes nodes for those pods, Karpenter will find a best fit instance type for them and run it. So just to walk through an example, if we launch a task that needs 8 gigabytes of memory, and that's specified in the @Ray remote decorator, you can say memory equals 8 gigabytes, and we don't have any instances that have 8 gigabytes, well, the autoscaler will still try to launch a worker pod to run that 8 gigabyte task. And then Karpenter will see that, and it'll see, oh, we have a pod that needs 8 gigabytes, but none of our nodes, none of our Kubernetes nodes have that. So it will scan the instance types available and find a best fit one for that. Karpenter can also use spot instances, or you can configure it to choose spot instances. So since these instances are really short-lived, it makes a good application for spot instances. And even if a spot instance gets terminated and the worker nodes running on that just suddenly disappear, Ray has built-in automatic retrying of tasks. So the tasks that we're running on that instance will just automatically get rescheduled. And that could mean bringing up another worker pod, and then just the cycle continues, like Karpenter will find a new instance to bring that up. So I took some screenshots of a demo, and so the demo will just have to be me talking through some screenshots. But initially, this is just, we saw this earlier. This is how you initialize Ray. You wouldn't call ray.init twice in the same script, but that's just for demonstration here. Ray.init without an address will create a local cluster, but you can also connect it to a remote cluster. And the reason it's localhost here is because I was port forwarding to the actual remote cluster, but just imagine any address here. And then I'm going to talk through 3 different helper functions just to make the slides shorter later as we use them. This helper is really just to time how long a block of code takes. So we can say with timer and some block of code, and we'll see how long it took. This one, it's a function that will return the instance type that it's running on. So this is how we can kind of see, okay, when we run a task, we can just see what instance type did we actually get that we were running on. And then this one will print the Ray cluster resources. So as we run a task and the cluster auto scales up, we can print the cluster resources like before and after to see like, what what are our resources now? Okay, so as an initial example, I showed this earlier, but this function, which we can think of as like preprocessing data, we say it needs 1 gigabyte of memory, 1 CPU. It just sleeps and returns the instance type. And it makes sense. It takes about 1 or 2 seconds to run, and it ran on a T3 2x large, so relatively small. Well, okay, and then continuing from there, we can print the cluster resources, and we see, okay, we have 4 CPUs, and in the bottom half here, there's some code to count how many tasks ran per instance type. So in this case, I'm running that preprocess function that I showed earlier, and I'm just running it 60 times, and it will run on that instance. You can see the counter, it says 60 for that instance type, but it only took 16 seconds. So that is expected, that if we're able to run 4 tasks per this instance type, then roughly 16 times 4 is 60 plus some overhead. So where it gets interesting is when we want to run a lot more. So the previous example might be like something you would write if you're iterating locally on your development environment. You don't really want to like preprocess a whole data set on your laptop because it would take a while. But then you want to use the resources that are available in the cloud. All you would have to do is change the ray.init line to the cluster address and not your local. And in this case, I'm demonstrating, okay, well, what if we want to run this 6,000 times? And we see that it launched some pretty large instances. And that's because those multiple pods in the diagram earlier, Karpenter will see them as a unit and find an instance type that fits all of them. It doesn't go and find an instance type for each pod. It will just find one instance type that can fit all of those pods. So in this example, we run 6,000 times, but we see a kind of distribution of like, okay, well, more ran on the larger instance because it has more CPUs. But overall, this took 50 seconds, so that's really nice. And now our cluster has 292 CPUs and 400 gigs of RAM. But if we stopped running things, then the Ray autoscaler will terminate or get rid of those Ray worker pods. And then Karpenter will see that these instances don't have any pods on them and then also terminate them. And all this is configurable with it's all configurable, like how long do you wait before you shut down. So another example I wanted to show is like, well, what if you want to use a lot of memory? So this, called preprocessed big data, is looking to use 100 gigabytes of memory. And just running it once, we see it chose an i4i.8x, and that was kind of interesting to me because I thought it would have chosen like an R4 since that's cheaper. But when I looked into this, the i4i in that moment of time had more spot availability. So by choosing this, it reduces the likelihood of getting interrupted, but it ended up choosing a instance type that was a bit more expensive. I think that's also configurable. You can choose like your spot allocation strategy, but just something it's just another configuration you can do with Karpenter. Well, now I don't know what I did because I can't go to the, okay. Another example with training, so, and this might be getting repetitive, but I'm just trying to like show you different scenarios of how you can specify resources in your function and just run it. Like it should be this simple. So in this case, we want to train with 4 GPUs. Again, I'm just returning the instance type, but you could fill it in with multi or like same instance distributed training. And we see it took a while for the instance to come up. That's why it took 178 seconds. But, oh yeah, actually I realized I made a mistake here. I actually ran with only one GPU in this example, and that's why the output says one GPU. I was initially trying to run with 4, but I had an issue because at the moment, when I was working on these slides, Karpenter had an issue with launching this, and it's not that I'm trying to say that Karpenter is like, you shouldn't use it, but that since it's newer, there's still some like unresolved issues, or it's still going through a lot of changes, so it's just generally unstable right now. But they have already also, like, they're very responsive and they've already fixed this issue, so if I did these slides like next week, then maybe this would have worked. So that kind of brings me to a few ending slides, but one of the takeaways is Ray and Karpenter are both relatively new. So there's a lot, there's some risk with being like an early adopter to some of these tools, because you're going to be faced with frequent updates or staying on top of what's not working. Maybe it's like, looking through their GitHub issues often, or even filing your own. So that's one consideration is adopting, tools like this that are still early in their own journey. Is it a good time to do it? And is that what you want to spend your engineering effort on? So, the rosy picture is it makes your life easier with everything that I just tried to show you, but like in reality, or at least in my experience, there have been bugs with getting Ray to work and getting Karpenter to work and putting it together. And like, for example, actually, at Rev, we're still in the process of migrating to this whole setup, because some of these issues that we didn't know before, and we're over our estimate for migration. But it's just worth asking, okay, so what I just showed you, is it going to work for you? First, it's like identify your needs and just make sure that you are addressing that and you are choosing wisely what you're going to spend your engineering effort on. The alternative is you can choose proven, maybe boring technologies, but their value is they are proven and they're stable, and you know what you can expect when you use them. Though the downside is they may not address some of the challenges that I showed earlier, like right sizing or being easy to use. So if we had chosen to use AWS Batch instead of Ray, it would have been more challenging to do that on the development side. Like, I can't just use a decorator and just suddenly have a function. Well, it would take a lot more effort to get something like that to work, and that's why we chose to use Ray instead. But if we didn't want to use newer technologies, then we might have to implement a lot of our own like tooling around it. But overall, like, choosing open source technologies has been nice because they have very active communities, and they are making updates. So it's exciting, but it's also a risk in terms of what you're willing to spend your engineering effort on. I have my demo code for what I showed earlier on GitHub if you do want to see it and if you do want to try it. But just keep in mind all the caveats I was just trying to explain earlier. And I want to end on this slide, which is going back to the original problem, like bridging the gap between your development environment and using the resources that are available in the cloud and trying to make that as easy as possible. This is what we had initially set out to do, and this is what we came up with, everything I showed you before. And there were some challenges with trying to adopt these tools like Ray and Karpenter because they're still new and they're also going through a lot of updates. But I also think, I guess we're pretty optimistic that they will get to a point where they're more stable, and also we can contribute to that. And I think that's why we ended up choosing to use them. So overall, it's up to you if the setup that I showed you would work for you. But that concludes my talk, and I hope you found something valuable from this.
There you go.
Hey, yeah, thanks for the talk. So why did you decide to go with Ray instead of Kubeflow or any other available?
Yeah, maybe we just didn't look hard enough into Kubeflow. My understanding of Kubeflow is it is a whole suite of tools, and we were only really trying to replace our cluster and like job runner, like batch or like large job runner. So right now we use something called SGE with AWS Parallel Cluster, and that is just the piece we want to try to replace. So it's possible maybe Kubeflow could have helped here, but it didn't seem like it would solve this very specific thing for us. Yeah. But I mean, like feel free to like let me know that I was wrong and like tell me how to use Kubeflow.
So Victor, you were talking about building versus buying something that is already ready and
Right.
and you said ultimately it's up to you, but a lot of time you have limitations with your engineering team. So what are some characteristics of this engineering team that you have found that would help you achieve the build part better based on open?
So that's a really good question. Choosing to build versus buy, and first of all, choosing to build versus buy, I think you should ask, is what you're building critical to your business, or is it something you can just like use a managed service for? Because when you build it, then you have full control over what you can add and take or not use, but now you also have to maintain it, and that's expensive. So if it's something that's business critical, then it's worth building, in my opinion. Now, I guess choosing what to build does depend on the skills that your engineering team has. And also maybe you could forecast, like if you know you're going to hire more for your team, then you can forecast what roles you will need or what skills you need for what you're building. But I would start with, does what we want to build solve a business problem or is something critical to the business first? And then look at what you want to build and what skills your team has and how you need to grow that team to build what you're looking to build.
Just had a question about autoscaling in Kubernetes and Karpenter. Can actually a whole stack be simplified and Karpenter removed entirely out of the scene? And can we just go directly with Kubernetes scaling?
So the Kubernetes cluster autoscaler?
Yeah.
Yeah, so Kubernetes cluster autoscaler and Karpenter kind of solve the same issues, but in different ways. And Karpenter is actually was designed to address some of the issues with the cluster autoscaler. Two issues are with cluster autoscaler, you have to define your instance types up front in groups. And that was, in this case, that was something we were trying to avoid, is we just wanted that to be automated, and that's something Karpenter can do. And another issue that Karpenter solves, or at least does better, is it doesn't use groups, and that makes it faster because it can just launch instances and manage them directly instead of trying to change a number on a node group and wait for the node group to launch a new instance. It may be less than a minute different, or maybe a few minutes, but that can be a long time when you're just waiting for when you're iterating or when you're waiting for a job to run.
Thanks. I just had a question about the kind of diversity of stuff that you can do with it more from a hardware perspective. So I kind of assume that a lot of the servers you're working with when deploying this would be obviously very homogeneous, but particularly for machine learning applications like NVMe drives and very fast model caching and things like that can vary from instance to instance. So have you got any insights on more the kind of complexities of especially big machine learning models on different hardware pieces where there's different physical storage drives or network drives attached and things like that?
Okay, so I guess you're asking how would we connect external storage to this cluster? Okay, so when we're using Kubernetes, you would have to create a persistent volume and mount your external storage through that. But then you could just configure that every pod that comes up will have those mounted. And that is something we had to do too, because we also run workloads that connect to like an NFS server, and we store some data there. So you would have to do some manual configuration of getting every pod to automatically mount that. And so to answer the question is like understanding how to create those persistent volumes in Kubernetes and then mounting them to the pods. But it's not quite, it's not something that I did in the demo.